So this video is in case you needed a refresher on how to solve spectroscopy. I'm just going to do two problems here, which I'll post on Moodle so that you have the hard copy. The first thing that you're going to get with your unknown experiment is the spectra with a formula. You'll have IR, carbon NMR, and proton NMR as well. And your job is to solve the structure using these three pieces of information, just like we did in 225. When you're given the formula, the first thing that you want to do is calculate the number of rings or double bonds using the formula. So for this one, I have 6 times 2. So it's the number of carbons times 2. We add 2. We're going to subtract the number of hydrogens, which is 12. Divide the whole thing by 2. I get 2 over 2, which equals 1 ring or double bond. So the ring could be a cyclic structure. Double bonds can be a carbonyl or can be a carbon-carbon double bond. So we're looking for at least one of those things in our structure. The next thing you want to do is look at the IR to see if there's any functional groups that pop out. The first thing that I observe here is that these peaks here, these carbon-hydrogen stretches, are less than 3,000. So I have sp3 CHs. The carbons in the structure are all going to be single bonds, or they will have carbon double bonds with no hydrogens on them. The other thing that I observe here is that I have a peak at this is 1617, which is indicative of a carbonyl. And if you wanted to look further, this could be 1500, which could be a CO stretch. So I'm looking at a carbonyl, and that is going to probably be my site of unsaturation since I have this double bond here. So IR is going to tell us about the functional group. The next thing to look at is the carbon NMR. I'm just going to label these A, so that I can assign these later to the structure. One thing that I noticed right off the bat is that this is very far upfield at 180. These types of carbons are typically ester carbons. So I have a C double bond to an O. And if I look at my formula here, there's 2 oxygens, so I've taken care of my 2 oxygens in the structure. I also notice that I have 6 carbons, which there are 6 in the structure, so there's no symmetry here. So that's what I'm going to get out of the 13C NMR. Now I'm going to look at the proton NMR, label these, and I'm going to make my table. So I have the proton shift, integration of each proton, which is given to you, the multiplicity, and I'm going to try to interpret information about the neighbor. But I'm going to start at the lower numbers. This is 0.9, that's proton E. Integration is 3H, multiplicity is a triplet, which I'll just put T. So that is a CH3. That sits next to a CH2. So that comes from the 3 minus 1 equals 2 neighbors next door. The next proton is D, which shows up around 1.3. That integrates to 2H. If I look closely at the peaks here, I have 1, 2, 3, 4, 5, 6. So that's a sextet. So 6 minus 1 is going to be 5. I have 5 proton neighbors next door. This is a CH2. Oh, it's probably a CH3 next to a CH2. My next proton is C. That's at 1.5. We'll call it that. This is 2H. This one has 1, 2, 3, 4, 5. This is a quintet. So 5 minus 1 equals 4 proton neighbors. So that would be a CH2 next to 2 CH2s, next to 2 CH2s, or it could be a CH3 CH2 next to a CH. Okay, so both of these have 4 neighbors next door. So we have to keep filling out our table to see what we can rule out. Proton B, 2.3, it's 2H. That'll be a CH2 next to a CH2. And then I have A, which is quite a bit upfield. That is at 3.7, 3H. It's a singlet. So I have a CH3 next to something. If I count up my hydrogens here, 3, 6, 7, 8, 9, 10, 11, 12. And my carbons, I have 1, 2, 3, 4, 5 carbons, which is okay because we know that one of the carbons is from this 13C NMR. If I look back at my table here, I'm going to figure out which of those pieces I can rule out. This one has a CH2 next to 2 CH2s, while I have a CH2 next to a CH3 and a CH. There's nowhere in my table where I have a CH, so I'm going to rule this one out. But I think that this CH3 next to the CH2 is the same as this one. So this is E, this is D. This is a CH2 next to a CH2, which fits these here. So I think this is C, so I probably have a D here. And this might be in the middle of those as well. So if I'm going to put my pieces together, I have a CH3, which was E, CH2D, CH2C, which is next to another one. It's probably next to B. So that's next to CH2B. So I have that 4-carbon chunk. So this one is B, and this is C. This is B, this is C. And then I have a CH3 next to something. The other piece I have is the ester. And then I have a CH3 next to something. If I look at this big chunk, all of these are filled octets. The only thing that's missing here is to connect this to something, this has to connect in that. So I think that this CH3 is next to this. So to put the pieces together, I have a 4-carbon chain, the ester part, and then I have that. I should go back and characterize. This carbon is the A carbon. The B carbon is this one here because it's a little bit more upfield. And then we have C, D, E, F. And then for the protons, this one is HA. Then to look at my protons, the one at 2.3, this one's HB. This is HC as it gets further away from the carbonyl, HD, and HE. So that's how you should annotate your spectra for the unknown and also to solve your structure. For the next problem, we want to go through the same process and first calculate the sites of unsaturation. We notice that we have a nitrogen in the formula. We have to do something a little bit different in order to get to the rings or double bond calculation. We're going to start the same with the number of carbons times 2. We'll add 2. We also add 1 for the nitrogen. Subtract the number of protons, and that's divided by 2. That comes out to 4 rings or double bonds. And if you remember from last semester, 4 rings or double bonds usually indicates a benzene ring. So we're going to look for a benzene ring. We're going to look at the IR now and look for what functional groups we have. Again, I'm observing here I have sp3 CHs. And because I know I'm looking for benzene, I can also see here that there are some sp2 CH stretches as well. And this looks kind of like teeth. This is out here at 3400, so I'm thinking that is an NH2. If I look at the lower numbers here, this is around 1600, which is not quite enough for a carbon double bond oxygen, but these look like benzene ring stretches to me. And this one here looks like a CO. Okay, so the carbon NMR, these all are in the realm of benzene rings. I'm going to count how many carbons. Let's see, I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So I have a little bit of symmetry. And this peak is a little bit taller, so that this is probably the peak that has 2 of the same one. Now looking at the proton NMR, so for E, that's around 1, 6H, doublet. This is CH3 next to a CH. We can't have 6 hydrogens on the same carbon, so it's probably 2 CH3 groups. This is the 2 minus 1. The next one is D, down at 3.8. And I'm going to observe also here that this is very far upfield. So the proton shift is high, which means it's probably next to something electronegative. If I zoom in here, I have 1, 2, 3, 4, 5, 6, 7 peaks. 7 peaks, that's a septet. So that's 7 minus 1, or 6. I have a CH next to 2 CH3s. So these two are probably the same fragment. At 5.6, there's a 2H and it is a broad singlet. This is probably my NH2 that I saw in the IR. At B, this is 6.3 to 6.5, we'll say 3H. It's kind of a mess. I'm going to call that a multiplet. These are our benzene protons. And then proton A, 7.0, that's 1H. And that one is a triplet. So I think I have a substitution pattern where if there's a triplet possible, that means it's next to two protons. So it's probably this one right here. This is probably proton D. And I don't know where the rest of these fall within this 3H, but there's 3 other hydrogens possible there. So tally up my hydrogens, 13 H's, which is what we want. Carbons, I have 6 in the ring, 7, 8, 9. So that symmetry that we see, I think it's these 2 carbons right here in the CH3, which is why we have 9 carbons here. So that accounts for that 8 carbons in the molecule. So my puzzle pieces are an isopropyl group. I have a benzene ring with a 1,3 substitution. I have an NH2, and the only thing I'm missing is an oxygen. So a place that could have the oxygen is this one right here, this isopropyl group, just because it's at 3.8, which is very high. An NH2 that you would see at 5.6, that's higher than you would normally see in NH2 peak. So I think that's on the ring. And then I have another group coming off of here. If I put the oxygen next to the ring and put the isopropyl group on there, that will fill my structure. So I'm going to go back and assign the carbon to each of these. So the one furthest, so the one that has the lowest number here will be H. The benzene carbons, the N is electronegative, which will move this here. This is probably A, this is B. Then we have C, D, E, F, just around the ring there. And this right here is going to be G, which is next to the oxygen. And to assign the protons, this NH2 here, this is A. That's HA. HB is around the ring. So this could be HB. There's a cluster of them. This one is HB. This one is HB. The one that was seeing a triplet, that one is HD. The one that was seeing the triplet is HA. This here is HD. And then on the end here is HE. So again, that is how you would assign the protons, the carbon, and the IR spectra for your NMR unknowns. Hopefully that was helpful.